Welcome again. I'm Giancarlo Guizzardi, and I've been organizing this together with Enrico Franconi, Thiago Salles, and Claudine Moraes. EROSS is connected to the Bolzano Summer of Knowledge, which is overlapping with the Bolzano Summer of Knowledge this week. So this talk is also a keynote to the whole series of events of the Bolzano Summer of Knowledge. And it's also connected to the 4 decades tradition of the International Conference on Conceptual Modeling, ER, which will happen online in the first week of November. So we'll continue to meet every Wednesday into ER. The computer science and information systems fields are replete with fundamental concepts that are poorly defined. For example, concepts like system, subsystem, module, object, interface, coupling, cohesion, hierarchy, input, output, environment, and decomposition are central to many theories in both fields, but inevitably, they have not been articulated rigorously. In the absence of carefully formulated foundations, fields are unlikely to progress quickly. We concur with David Parnas, who observes the use of fuzzy terms in computer science is not merely sloppy wording. It prevents the systematic analysis made possible by precise definitions. I concur with David Parnas, but also with Yair Wand and Ron Weber, who wrote this 30 years ago. And I couldn't agree more 20 years ago when I read this seminal paper. So I'm extremely happy today to have here with us Yair Wand, was until very recently a CANFOR Professor of Management Information Systems at the Sauder School of Business, University of British Columbia, Canada. He's a key international figure in the areas of conceptual modeling, information systems engineering, enterprise modeling, management information systems, requirements engineering, and so on. He's mostly known by his pioneering work in the area of ontological foundations for conceptual modeling, in particular by what came to be known as the BWW ontology, foundation ontology. So he's the first W in BWW. He has published extensively in these areas in top journals such as Nature, Communications of the ACM, MISQ, and so on. He has also served as associate editor for journals such as the Journal of the Association of Information Systems, again, MISQ, Communications of the ACM, and etc. Finally, he was granted a number of awards throughout his career, including the UBC Killam Research Award and the Senior Research Excellence Award, also by UBC. And finally, he was granted the greatest honor, bestowed by this community, which is the Peter Chen Award Winner. So to tell us about the importance of theoretical foundations for conceptual modeling, in particular about classification, the role of classification in scientific theories, I'm very happy to invite today Yair Wand. Yair, thank you very much for being here. Welcome to EROSS.
Well, first of all, lots of thanks for the people who studied EROSS. It's really great, and I'm very happy to present here. We had a little bit of technical problems, which I cannot name, but you can hear more about it in direct communication, what happened here. Anyhow, so I'm going to describe something which came as a surprise to us a few years ago. We were working on trying to classify data and conceptual models. And as we worked on it, we realized that data are not only unique to IT, it's much more general. So we tried it in the context of some theories of classification in general, and it seemed to be working nice. So that's what I would like to discuss today. So a little bit of the background. I would like to explain how we got to this background, what we will try to show. I would like to make a distinction between categories and classification, because there is some difference there. I would like to explain how it might fit theory by showing an example of Pluto, our planet. I would like to discuss the aircraft example to show in more detail how it works. And then I like to use electromagnetism as a way to show how it works without getting into the formulas. So the trick is to discuss electromagnetism without getting into the formulas. Do I have to do it in 1 hour or less, or how much time do I have?
Yair, just go ahead. Feel free to deliver your message.
Okay, I will go. About 30 years ago, Jeff Parsons and I have been working on the meaning of classification. We used, it was very important, cognitive use. And cognitive use of classification means that you classify in order to obtain what we call economy, efficiency in storage and retrieval. But more as interesting is the idea to infer. In other words, if something belongs to a class, you may infer more about its properties than you need to assign it to the class. And the idea, of course, we try to apply to organization of data. Then we included it in a more higher level in conceptual models. But as I said before, the idea of data is not unique to information technology. And I would like to describe our generalization to the theory of science. Now, is it useful? We hope to show this. Now, categorization is a very useful approach to organize facts around us. You know, animals, of course. We have a big thing about how to classify, and not just animals, all items that exist around us in nature. Planets, whatever. However, classes, as we say from cognitive theories, should be more than a category. A category that enable us to infer, or we call derive, more ideas about an instance. Now, I would like to give a very simple example. Things in my office is a category, everything that belongs to my office or not. However, can we say that things in my office is a class? What if in my office we also have the rule that nobody, except me of course, can do anything with it? Then, knowing that something in my office, we have an additional fact, the fact that nobody can do anything. So now what was category, things in my office, we know one more thing about items, nobody can touch them except me. Now, the question is, if a category is not a class, do we learn anything from it? Of course. It's a very short way to describe lots of items around us using a much simpler term of a category. So it's used to, of course, in language, we use it a lot. And without having categories, it will be hard to do things. However, categories does not give us additional ideas to infer more. Now, we have thought about how to extend the idea. We formally define them, which I'm not going to do today, and we are going to describe rules not about one class, but about collections of classes. And then we found that it provided a way to think about not just data and conceptual models, but we think about general science. Fundamental concepts, and they will be very helpful for us. Phenomena is anything of interest that can be described by predicates or factual statements. Anything about thing we can say, we can give attributes or predicates. We use it also, we call it instance, not just phenomena, it's just a name. Attribute is a statement that is true about the phenomenon. We say that the phenomena possesses the attribute. It has several attributes usually, and it possesses them. Category, you take all the attributes that an item has, that the phenomena has, or an instance, and they say all the attributes together creates a category. And here comes the interesting thing about the class. It's a category. In other words, there is a bunch of attributes that define you as a member of the class. However, when we look at all the attributes, you see there are two parts. There is a minimum part which requires it to be in the class. You don't need to have all the attributes to assign a phenomenon to a class, only some of them. And by being a member of the class, all the other attributes can be derived, can be inferred, can be assumed to have, even though you only use some of the attributes. Now, without an example, it's hard to show. By the way, I just want to know that my voice comes okay. Anybody can make a comment to me?
It's great, Yair.
Okay, not too loud, not too, okay, good. Okay, one of the best examples which accompanied us from the 1930s, would you believe we're almost 100 years after that, is the case of Pluto. But before we discuss it, I would like again to discuss classification again. Each class has instances. If a class has no instances, it's of no interest to us. And there exists at least one phenomena that had all the instances. Otherwise, the class is of no interest. The class is defined in terms of all attributes, but again, and I'm repeating what I said, it's partitioned into two parts. A part which is enough to assign to the class, and a part that can be derived from it. So the additional attributes can be derived without using it for assignment. And this ability to derive, it will be very important for us in the scientific context. Okay, so each attribute of the category, which is now a class, is either what we call the base, assigning to the class, or derived. Now, why is it so useful? And the first example we'll use is our planet Pluto. The old definition of planets was round, pretty large, and going around the sun. This was our own definition. And is it a category? Is it a class? And that's the interesting thing. If we cannot say anything more, it's just round, pretty large, and going around the sun, then it's a category. However, if we can say about, and let's see whom, we can say all of them that all of them are orbits in about the same plane, and no orbit of a planet touches the orbit of another. And these are something that was known for all, now I'm saying 8 planets until the 30s. We will call this inferences, we can infer, or we will use later the word laws, and can be added to all planets except, we'll see Pluto, until the 30s, okay? Well, as I said, Pluto was identified, and pretty late, in 1930, and actually they were looking for another planet, and they found Pluto, which was completely different. When Pluto discovered, something happened. Its orbit did intersect the next farther a planet of Neptune, and moreover, it was not co-planet with other planets. But still in the 30s, we said we had 9 planets, right? However, and pretty late, I think most of us were alive then, all of us, I think, the International Astronomical Union, and by the way, it's a decision. Please notice that the decision decided that Pluto is not a regular planet. They call it a dwarf planet. And they said, okay, now we have to say what planets are. The object must be in an orbit around the sun. It must be massive enough to be rounded by its own gravity. And here is the third, all its environment should be cleared. And apparently in Pluto, it's not a cleared environment. Since Pluto does not provide 3, only the first 2, they wanted to call it dwarf planets. Before we continue, I would like to show you the definition from Wikipedia, and I purposely checked it yesterday. On September 13, 2006, the International Astronomical Union decided that Pluto, much like other objects that were found, Eris and Dysomnia, belong to what we call a minor planet. Now, is it a minor planet? Is it not? Please notice they decided, and that's an important issue. So when we go back, since Pluto does not provide 3, they decided to call it a dwarf planet. However, if you define planet as almost circular objects that are in orbits around the sun, then it's a planet. So it's up to you to decide whether Pluto is a planet, a dwarf planet, or something else. It's completely a human decision based on what you don't want to do with the class. And that's the important part. I would like to briefly mention collections of classes, and I would like not to be too technical about it. There are 3 conditions to form not one class, but many. If 2 classes have similar properties and what we call inference, then you can create a higher level class. If 2 classes have the same, then we create a higher level. Each class in a class structure must provide at least 1 inference, not otherwise provided. If it provided the same inference, it's not a new class. And you only add class if it provides these inferences, okay? Only if it provides additional inference. And this picture shows this class here is a subclass of this and this. It must provide additional inference, otherwise it's not a separate class. And we will see more examples. I will continue from here. Now I like, and that's an important case, it's the aircraft case. This case we used as an example to see how categories and classes work. We like to describe what an aircraft is. We start with a diagram showing the main transport classes. So in air, on land, and in the water. Aircraft, there are 3, it's just make it simple, it can be more complicated. Usual regular aircraft, helicopter, and glider. We will assume a new fact is found and see how it can be sorted out into a class structure. In other words, we will have aircraft, we will addition, and we say, okay, in one case of aircraft, it will not be a class, it will be a category. Nothing new is found. And then we say, okay, can we make it a class? And then I'll explain the general rules that were applied. So here are all the, just my way of describing it. It's a class can be a general class can be in medium and has features. If it has wheels on the left, then it's a land vehicle. In the middle, if it has sails, then it is in water. And on the right, if it has air, if it has medium air, then it must be a general aircraft or flying in the air. Just for the fun, I looked at the aircraft and I partitioned it. On the left, I said, depending on the fuel in the motor, it could be left gasoline or jet. There is a difference between the what we put into regular aircraft and to jet aircraft. It's gasoline and jet aircraft. I just did it for the fun. On the right is interesting. We have 3 types of aircraft. One is directly using fixed and no propulsion, and so and it says it goes on air. So if it has fixed and the propulsion is none, then it goes on air and that's a glider. In the middle, I said, if we use motor and there is fuel, then what happened? When we go to the right, we see there are two kinds. Helicopter, it's a rotating wings, and if it's rotating, it must be motorized. In other words, there are no helicopter that doesn't have a motorized. So motorized is an inference. We don't have to say how it motorized. We say it's a rotating wings, and automatically it must be motorized. But then here is an interesting thing. If airplanes are fixed and motorized, then there is nothing new. We don't know anything new about an airplane. It has to be fixed wings, it has to be motorized. Otherwise, it's not an interest. So the question is, okay, so airplane is a category, which is a category of motorized aircraft. So does it make sense? Well, it's up to us to decide. And what I want to show how we can add properties to airplane to make it interesting as a class, not as a categories. Now, what we can do, an aircraft with fixed wings and motorized be a class, not a category. If more properties fixed be a class, if more properties must be included. The two properties are not enough. Okay, runway, where they can start and end the travel may be useful. So if we added runway to fixed wing and motorized, we can use runway as an inferred, or we can use it to infer something else. I will use the first case. We use case one. A runway is necessary to know the possible routes of an aircraft. In other words, it must have runways to depart and arrive. Could be very simple runways, could be on the grass, but it must have it. If we add routes include runways, then we can add the inference. If it's motorized and fixed wings, the routes must include runway. So in other words, now we have a base of the first two, fixed and motorized, and the inference, if it's fixed and motorized, it must start and land on a runway. Is it going okay? I don't know. I just want to make sure that it's okay.
It's all fine, Yair. Don't worry, we'll let you know.
Okay, thank you very much. Unbelievable how it works. That's amazing. Okay, I like to show you the full picture only of the aircraft. I didn't show the other ones. And what you see, now airplane became a class because if we know that it's fixed wings and motorized, it must start and end on the runway. As I said, this is a simple way, but we now call it a class or a subclass. And what have we learned? The fact that it's fixed and motorized, we know automatically that there must be a runway. We don't have to include it at what we call base to make something an aircraft. Fixed and motorized is enough. Okay, what can we do in addition? And that's an interesting thing. We already had motorized and fixed wing in runway. Routes include runways, we know that. However, we know from experience that if motorized and fixed wings and it lands and starts on water, the routes include a body of water. In other words, if it goes in water, it must start and end on water. Now, a new possibility arises. We have two properties, runway and water, and therefore we say fixed wing motorized, we have facility. Is it wheels or is it floats? And we have routes. Does it start on land? Does it start on water? So what we have, the facility, the fixed wing and motorized with the facility, wheels or floats, we know the routes are decided. So now we have two classes, one fixed wing and land, another fixed wing and water, and look what we did. This is now added to fixed and motorized, not one part landing, but also the routes, which it's supposed to. And we say, we know where it's land, water, or, sorry, I'll show in a minute what happened. If it has floats and water, and it goes on water, the floats define water. If it has wheels, then the wheels define runway. So we took two classes, one land on land, one land on water. We generalized them as number 3, have 4 different parts for the category, but only 3 are based and one of them is determined. So this may be very useful. And I purposely use the aircraft example because this doesn't sound like science, although it is. And it's a good way to see what we are doing. What I like to do now, and this will take us a few minutes to understand what we have done here. And this is the next table. Okay, so it's a little bit more complicated. And can you see my mouse? Do you see my mouse moving? Or not?
Yes, we do.
Okay,
yes.
That's very good. I should have made it a little bit bigger, but I think it's big enough. Okay. The rules are, if the inference cannot be justified, we'll see in a moment. If the category seems to be important, we like to make it a class, and there are 2 ways to make it. We call it prediction and explanation. And the last is, if there are 2 classes that meet the additional properties, we sometimes generalize them. That's what we did here. And I would like to say, if the inference is not very important, we remove it. We are not interested in the inference. And if any class became of that inference unique and we are not interested, that's it. The class is out. It's not part of classification. We might end up losing some properties because there is no inference of interest. If the category seems important, we'll try to locate part of the category of the original class. Okay? If the subcategory has an inference with a newly found property, it is in a class. In other words, we have a subcategory that has inference, and the inference tells us something about new properties. Can we make it now a class? So basically, we now define the original, the new found property, maybe new properties. We now have a bigger class, not the original, and maybe new properties, but also the newly found properties. Prediction. The original becomes, perhaps new properties become the new property. The new property is predicted. It's like the aircraft, where it lands and takes off. It's predicted by other parts. That's what we see here. Another example, which I didn't show, we take landing in water or on a land, and we make it to define other properties. For example, wheels or floats. We could have done this as well. I haven't done it. And finally, when we have the case of aircraft with land and with water, we generalize it, and we said we have no land and water. We have a general way of landing and taking off, and this can be sub-partitioned into classes, into water and lands. I'll go back here, and that's what we see. This can be generalized in a more general way, and there are 2 types of aircraft, on water and on land. That's what we see here. So this was looking at what we call more conceptual models, but we use an aircraft case to explain it. And we have papers that describe it. If anybody interested, I will list them later. What is interesting now, I want to discuss classification and science in general. And it's very important that scientific theories about not objects, but relationships of objects. The objects in a scientific theory do not have to be physical. For example, in electromagnetic theories, it may be forces, and actually Maxwell, who originated the full theory of electromagnetic, called them fields. We now talk about more forces, but they're just a name. Science begins, and that's very important, always with observations. If there are no observations, then we cannot say anything interesting. The observation I summarized in terms of categories. Please notice categories, we don't have a law. However, what makes science really interesting, if we know more about the items, then requires to categorize them. In other words, if we know more by using less properties. That's very important. The ability to know more is what gives us what we call in science laws, define more properties that we don't have to classify the objects. Okay, I would like to mention it again, that what makes science interesting, we know more about items than to categorize them. If you think about the planets and Pluto, if we have the first 8 planets, we know additional things that we don't have to measure. If they have the 3 properties of make it a planet, then the planar and no trajectory orbit, an orbit of one not linking to the others, automatically makes it a planet, although we don't have to indicate anything. Knowledge of infer, we call it in physics, not just in physics, a law, a relationship among attributes of a measured things. By the way, similar classes can sometimes have a higher level class. We are not worried about it now, but sometimes we found similar classes when we have the same inference, then we generalize it. The claim, if a category appears of interest, there are laws related to it. In other words, science is of no interest if we cannot say more things about it. And that's a very strong claim. Whether it's correct or not, that's left to the audience. Otherwise, if we cannot indicate more about the properties of a type of object, then it's a category, it's not a class. It's nice to have it. We have a good way in language to describe it, but we don't know anything more. And we claim this is a very interesting in science. What I like to use is electromagnetism. Now, what I'm going to show now, although I'm going to mention the mathematical properties, you can completely follow it without understanding anything in maths. All you have to understand what it really says, and I will show it to you. However, I will mention that before Maxwell appeared as a research scientist to study the electromagnetism, Coulomb links charges and electric forces, and we say there is a law, Q and E, and I don't worry how it looks. We know that charges cannot move around unless we change how much Q we have. Without moving Q, there is no current. And it was known for a long time, since the Greeks, or maybe earlier, that there is a law. There is North Pole, South Pole, that together there is no monopoles. That's basically, and I'm not even showing how it does. This was known before. During Maxwell's time, Faraday found that if you change magnetic field, you generate electric field. By the way, Faraday and Maxwell knew each other but at that time Faraday was quite a few, 20 or 30 years older than Maxwell, but they still knew each other. Current can move magnets. This was found by Ørsted, a Swedish researcher, and he found that if you move current, if you have current, you can change the direction of a magnetic needle. We all know it. Ampere found the empirical law that describes it. Finally, and that's very interesting, Maxwell added what he called displaced current. Displacement current was a very simple thing, but there was no way to measure it in Maxwell's time. You can change in time the electric field and it generates a magnetism. So changing electric field in time can change magnetism. Now, why Maxwell couldn't see it? It took Hertz about 20 years later, 25 years later, to show it physically. And at that time, Maxwell was already dead, so he couldn't see the actual empirical validation of what he claimed. But he claimed this. Now, I would like to show for those who did study electromagnetism very quickly, just to have fun, the formulas. And the formulas is Coulomb charge, that's electric field. This is a current, that's not, it's current density. We know that there is no current without moving electric charge. We know that the diversion, this one is 0. I don't want to get into the mathematics. The kernel of E is related to B. We don't care about it, but I would like to make one thing interesting. This way, which all of us who learned electromagnetism, whoever did, we don't know, but this is not the way Maxwell did it originally. It was changed, and that's an interesting proposition, by Oliver Heaviside. Oliver Heaviside lived from 1850 to 1925, and he did change Maxwell mathematical analysis. He didn't correct it. He just found much better way to describe it and make it much more general. And he did it without ever studying physics and electronics directly, but he did an amazing job. But so that's why I wanted to mention that this one is not the original Maxwell. Maxwell did it in a different way. It's interesting to read, but okay. Now, we are not caring about the mathematics. What I like to show, the top part is just saying what it means. The bottom part, I added the mass. You can disregard the bottom part. The top part is that charge and force are related. If you know the charges, you know the electric force. And that's called Coulomb, and that was done in early 1800s. Then we know that current cannot happen unless we change how much how much charge we have. If we don't change charge, there is no current. That's known. And finally, it is known for a long time that there is no separate north and south poles. They go together. These are the three. So the law is, if you have B, then it automatically goes to 0. There is no left or right, north or south monopole. We know there is no J unless we change current, and we know there is no electric force. I mean, electric force is related to current. So this was known when Maxwell started learning about it. And then during Maxwell's time, and please disregard the mass. I put it here for the fun, but we don't care about kernel and divergence. We don't care about it. What we know that based in Maxwell's time, there was a law of Faraday that if you change B, you get electric. And of course, this is how we get electricity at our home. Of course, we change B magnetic field, and we get electricity. We also, what Ørsted found, that if you current can move around magnetic fields. We know that. We know it in a simple experiment. So this was known. Okay, the category inherits all the laws, and it had a new law. This is a new law compared to here, and this is a new law. Faraday creating electric for magnetic, and Ørsted creating a moving B because of current. It was physically found, for things that were found physically. But it shows more links. So we have these three categories: Coulomb, current, and magnetic field, and we added two more. Now, what was interesting, and that was really Maxwell's, one of the great things Maxwell did. He did lots of other very great things. He actually started the first color photographs. People don't know it, but the first current photographs were based on his idea. He didn't start it, but he did the first colored photographs. And that's around 1860, very early, even before that. So again, Coulomb, you don't have current unless you change Q, and the B must be north and south go together. They don't have one north or one south. And of course, the original that Faraday found, you change B, you get electricity at home. And if you have the current, then you can change the direction of magnetic field. This is known, kids learn it. But Maxwell asked interesting, if we put all of this together, the current, the charge, the magnetic force, the electric force, the magnetic force, together, do we know anything new? And here comes the interesting proposition. LEQ came from here. JQ came from here. B0 came from here. EB came from here. BJ came from here. There was nothing in addition known when you put charge, electric, current, and magnetic field. When we put them together, nothing new, because all this was known in advance. So putting all four together did not make it a class. It was a category, okay? There is no law that combined in addition. So basically, I'm showing it here, but then that Maxwell came, and that was the idea. He said, there is one more thing that I claim should happen. And again, don't pay attention to the math. If you change E in time, you generate magnetic field. Okay, we knew that if there is current, we generate magnetic field. But if you change E in time, you generate magnetic field. Now, for Maxwell, it was done completely theoretically. Completely theoretically. He did believe in ether, by the way, but that's a different issue. But he showed theoretically that this can happen, completely theoretically. Now, what happened now? Now we connected one more, E and B. E from here, B from here, we connected them together, and now we have a new law for all forces, magnetic and electric. This was new. So basically now we say the base, current or changing of E creates B. So this was a new law that did not exist before. He added the changes of E in time generate magnetic field. Results. Okay, now he said that the base of B can generate by current, which Ørsted found. However, if you change E in time, when I say changing E, it should be in time. Mathematically, the curl of B is this, but we don't care about this. What we care that B is related by mu0 and epsilon 0 to the changes of E. And again, until Hertz's time, in the late 1880s, it was not known that this can be done, and Hertz has shown it. Changing of E in time generate magnetic field. Now, what is very interesting, mu0 and epsilon 0, mu is called permittivity, mu0 is called permeability. These are two things that can be measured, and I'm going to mention who measured them. That's very interesting. And so these values were known. So when Maxwell multiplied them, he got 1 over c squared. You know what c is, of course. Light. So he found when you combine these, which were measured completely empirically, the multiplication gave you 1 over c squared. So he said, oh, there is a wave here. If we allowed the magnetic field, the electric field to change in time to generate magnetic, then magnetic can generate electric, electric can generate magnetic, and this can be moved at this speed. That was, and this is the emergence of electromagnetism. I do want to show something very interesting that maybe not everybody knows about it. I didn't know about it when I studied physics quite a few years ago, and here it is. In 1856, two German researchers, Kohlrausch and Weber, found that they demonstrated the ratio of electrostatic to electromagnetic unit matched the value of the speed of light. So the fact that Maxwell found it, it was known empirically. Weber and Kohlrausch measured empirically with a very relatively simple experiment, what is called mu0 and epsilon 0. And when they multiplied, they got the speed of light. This find led to Maxwell's conjecture that light is an electromagnetic wave. It also led to Weber development of electrodynamics. Okay, actually, in their paper, they first used the word c to denote the speed of light. So even though Maxwell explained why it happens, and that was extremely important, there were some original ideas that it might happen. So that's what we found. By the way, there is a story about a journalist talking to Einstein and said, oh, you had your theory of relativity by standing on Newton's shoulder. And Einstein looked at him and said, no, no, I stood on Maxwell's shoulder, because Maxwell showed that that was very important to show things that came from Maxwell. Okay, I would like to summarize by two things. First of all, category is a list of properties. Classification, some properties can be derived. So a class provides more than a category. A category is good for short, efficient description. Without category, we can't use language. That's very clear, but it doesn't tell us new things. Classification means there should be a reason for classifying. If there is no reason, then the category does not provide new values. It doesn't predict new attributes. What is allowed the inference depends on what we want to do with the class. Applying the principle to science, we find that when the category is of value, there is a law to justify it. In other words, value, it means from a scientific point of view, we know more than to measure just being in the category. It's a higher level abstraction. Actually, by combining laws, we can generate higher level views. We didn't go into details. And we did show that electromagnetic classification can be described in these terms. So maybe it's a good way to think how science progresses. Okay, questions and comments. Oh, by the way, just people who are interested in some description, the last 3 have been published, the first is being written, and we are going to send it soon for publication.